everybody. My name is Yo, Mahan, Tim, my brothers. How we doing? Right. All right. We are back. Hello, everybody. Hey, Miss Kitty. All right, you guys. How's everybody doing? I hope you're having a good day so far. We just uploaded a project demo of our portfolio website, so go give that a check. We're going to also update our website here really quick because we have to do that. So let's go into our MD portfolio website. Let's go onto here. Let's go get status. Ooh, whoa. Nope. Not there. Get status. YouTube ad because double ad.
We're low on Pampers. Target run?
I'll go.
Wait, what? How'd you do that?
I have a...
I've recently come to learn that a lot of founders and marketers...
I'm not doing that. Okay. We're gonna check out our dev branch. Okay. We need to go to our projects page. We have professional portfolio website. And we're going to put a project demo link here. We're going to grab that from our most recent upload. Okay, where are you? Go on. Channel. Videos. Hello, everybody. Copy. Paste. This needs to be an embed link. Okay, that's right. I need to go. So, should we not even check? We'll say npm run dev. Looks good. Okay, let's push it up. Oh, whoops. I don't mean to go back that far. Alright. Add project Give it a second here to push. Woo! There it is. Nice. Project number 5 on the board. Nice, guys. How's it going? What you guys doing tonight? How you guys doing? Oh, the music's really loud. Let me turn it down. Okay. So we want calculus. All right. Let's see what we can do here. With some calculus. Let's try to learn some calculus. Let's try to learn some calculus. All right. We're on lesson 6 here.
1 of 6x.
Limits by direct substitution. Okay. Yeah, I guess that's right. Okay, a function. Okay, here we go.
Squared plus 5x minus 1. Now, the first thing that might jump out at you is this right over here. This expression could be used to define the graph of a parabola. And when you think about this, I'm not doing a rigorous proof here. A parabola would look something like this, and this would be an upward opening parabola. Looks something like this. It is this graph visually is continuous. You don't see any jumps or gaps in it. And in general, a quadratic like this is going to be defined for all values of x for all real numbers, and it's going to be continuous for all real numbers. And so if something is continuous for all real numbers, well then the limit as x approaches some real number is going to be the same thing as just evaluating the expression at that real number. So what am I saying? I'm just going to say it another way. We know that some function is continuous at some x value at x equals a if and only if, all right, that is if and only if the limit as x approaches a of f of x is equal to f of a. So I didn't do a rigorous proof here, but just it's conceptually not a big jump to say, okay, well this is just a standard quadratic right over here. It's defined for all real numbers, and in fact it's continuous for all real numbers.
Yeah.
And so we know that this expression, it could define a continuous function. So that means that the limit as x approaches a for this expression is just the same thing as evaluating this expression at a. And in this case, our a is -1. So all I have to do is evaluate this at -1. This is going to be 6 times -1 squared plus 5 times -1 minus 1. So that's just 1. This is -5. So it's 6 minus 5 minus 1, which is equal to 0. And we are done.
Okay. Simple enough. Okay, let's go. Let's try some practice problems here. Okay. Okay. -25. Five times -5 -25 plus a positive 4b -21 divided by -5 plus 8 would be +3. So it would be -7. Is that how you do negative here? Alright, +4 divided by divided by no, let's go back. Can I go back to the previous one? The 21. Yeah. Okay. 2 times 6. 12 plus 13, 25, square root of that. -3 squared is 9, minus -3, so plus a +3.
This summer, a sweet and juicy kiwi mission awaits, now spooning everywhere. The Jeep brand has always stood for American freedom.
Let me skip.
Now we're standing with you with Employee Pricing Plus.
So -3 squared is right, is 9, less a -3, so we're at 12, so this is 11.
Let's see if we can figure out the limit of x over natural log of x as x approaches 1. And like always, pause this video and see if you can figure it out on your own.
Natural log of 1 is 0, right? So you can't do that necessarily. So how is he going to do this? Is he going to plot it?
Well, we know from our limit properties, this is going to be the same thing as the limit as x approaches 1 of x over
the limit
limit as x approaches 1 of the natural log of x. Now, this top limit, the one I have in magenta, this is pretty straightforward. This, if we had the graph of y equals x, that would be continuous everywhere. It's defined for all real numbers and is continuous at all real numbers. And so if it's continuous, the limit as x approaches 1 of x is just going to be this evaluated at x equals 1. So this is just going to be 1. We just put a 1 in for this x. So the numerator here would just evaluate to a 1. Find continuous at x, then this equals 1. And since it is continuous at x equals 1, then the limit here is just going to be the natural log evaluated at x equals 1. So this is just going to be the natural log. To the 0 power is 1. So this is all going to be is 0 log, the natural log of 1, which of course is 0. E to the 0 power is 1. So this is all going to be equal to, if we just evaluate it, 1 over 0, not defined. Evaluate it like this and we get 0, which are done.
Does not exist. Okay. Cool. Easy enough. Ooh, 4 more questions here. Let's go. Okay. The limit as x goes to 1. So 1 minus 11 would be -10. 1 plus 7 would be 8. 5 over 4. Sheesh. Find the limit as x goes to -4 of this. Okay, so 16 less 15. -4 squared is 16, so this limit does not exist. Find the limit of 3x over x minus 2 as x squared plus 2. 12 over 2 times 6, 12. So 1. What you doing, Miss Katie? Got Kitty jumping up. Four over 0.
What we're going to do in this video is think about limits involving trigonometric functions. So let's just start with a fairly straightforward one. Let's find the limit as x approaches pi of sine of x. Pause the video and see if you can figure this out.
Well, isn't this...
Well, with both sine of x and cosine of x, they're defined for all real numbers. So their domain is all real numbers. You can put any real number in here for x, and it will give you an output. It is defined. And they are also continuous over their entire domain. In fact, all of the trigonometric functions are continuous over their entire domain.
Yeah.
And so for sine of x, because it's continuous and it's defined at sine of pi, we would say that this is the same thing as sine of pi. And sine of pi, you might already know, is equal to 0. And we could do a similar exercise with cosine of x. So if I were to say, what's the limit as x approaches, I'll just take an arbitrary angle, x approaches pi over 4 of cosine of x. Well, once again, cosine of x is defined for all real numbers. X can be any real number. It's also continuous. So for cosine of x, this limit is just going to be cosine of pi over 4. And that is going to be equal to square root of 2 over 2. This is one of those useful angles to know the sine and cosine of. If you think in degrees, this is a 45-degree angle. And in general, if I'm dealing with a sine or a cosine, the limit as x approaches a of sine of x is equal to sine of a. Once again, this is going to be true for any real number a. And I can make a similar statement about cosine of x. Limit as x approaches a of cosine of x is equal to cosine of a. Now, I've been saying it over and over. That's because both of their domains are all real numbers. They are defined for all real numbers that you put in, and they're continuous on their entire domain. But now let's do slightly more involved trigonometric functions, or ones that aren't defined for all real numbers, that their domains are constrained just a little bit more. So let's say if we were to take the limit as x approaches pi of tangent of x. What is this going to be equal to? Well, this is the same thing as the limit as x approaches pi. Tangent of x is sine of x over cosine of x. And so both of these are defined for pi. And so we could just substitute pi in, and we just want to ensure that we don't get a 0 in the denominator, because that would make it undefined. So we get sine of pi over cosine of pi, which is equal to 0 over -1, which is completely fine. If it was -1 over 0, we'd be in trouble. But this is just going to be equal to 0. So that works out. But if I were to ask you, what is the limit as x approaches pi over 2 of tangent of x? Pause the video and try to work that out.
Okay, so the limit...
Well, think about it. This
tangent of x of pi over 2, well, this would be... Well, obviously 0 over cosine of... What is the...
is the limit as x approaches pi over 2 of sine of x over cosine of x. Now, sine of pi over 2 is 1, but cosine of pi over 2 is 0. So if you were to just substitute it in, this would give you 1 over 0. And one way to think about it is pi over 2 is not in the domain of tangent of x. And so this limit actually turns out doesn't exist. In general, if we're dealing with sine, cosine, tangent, or cosecant, secant, or cotangent, if we're taking a limit to a point that is in their domain, then the value of the limit is going to be the same thing as the value of the function at that point. If you're taking a limit to a point that's not in their domain, there's a good chance that we're not going to have a limit. So here, there is no limit. And a way to deduce that is that pi over 2 is not in tangent of x's domain. If you were to graph tan of x, you would see a vertical asymptote at pi over 2. Let's do one more of these. So let's say the limit as x approaches pi of cotangent of x. Pause the video and see if you can figure out what that's going to be. Well, one way to think about it, cotangent of x, it's 1 over tangent of x. It's cosine of x over sine of x. This is a limit as x approaches pi.
I remember my pre-calculus stuff.
And
it's been a long time, boys.
Pi in the domain of cotangent of x? Well, no. If you were to just substitute pi in, you're going to get negative 1 over 0. And so that is not in the domain of cotangent of x. If you were to plot it, you would see a vertical asymptote right over there. And so we have no limit. So we have no limit. So once again, this is not in the domain of that. And so good chance that we have no limit. When the thing we're taking the limit to is in the domain of the trigonometric function, we're going to have a defined limit. And sine and cosine in particular are defined for all real numbers, and they're continuous over all real numbers. So you take the limit to anything for them, it's going to be defined, and it's going to be the value of the function at that point.
Gotcha. I want to take his cotangent example really quick.
Is in the domain of
Will it go down? Come on, go down.
the trigonometric function, we're going to have a defined limit. And sine and cosine in particular are defined for all real numbers, and they're continuous over all real numbers. So you take the limit to anything for them, it's going to be defined, and it's going to be the value of the function at that point.
Hey Harry, how's it going, dude? Welcome back in, my friend. All right, let's try some of these trigonometric ones. These might be a little bit more challenging. Okay, cotangent. Okay,
Let's think a little bit about limits
of
piece.
Okay, cotangent of x as x approaches 0. So we want to just take the cotangent. Is that no, that's antangent. Is that atangent? Oh, I can't remember. Anybody remember how to do cotangent? Oh! Is this of 0 equals to 0? Let me open up Desmos. It's undefined. So let's look up cotangent of x. Let's see. So at 0 we have an asymptote. Okay, so that's why we're undefined. So how would we be able to do this on the, so even though it gives us 0 here on a calculator, we can't necessarily, it doesn't say undefined. Can we say, okay, let's keep moving. Okay, the sine, so let's plot sine x. We know that sine x is continuous for all real numbers, so we can input pi over 3 into sine x. And what do we get for this? 0.86. Okay, which is, oh boy, it's not half. It does exist. Square root of 3, I want to say what happens? So, what if I say pi over 3 here? Pi over 3. I get 0.88. Or sorry, 0.86. So I freaking suck at school converting. So 0.86. We know that. What is square root of 3? Let's do calculator. We have a square root on here? No, we don't. So it'd be square root of 3 over 2. Keep the tunes rolling. Okay. Cosecant of x is pi over 4. So if you look up cosecant pi over 4.
Hyperfocus is the tool.
It is
of
defined 1.4.
But the problem with hyperfocus is that I would
The hyperfocus. So it's not that. We did that one last time. It's not 0 point. It's less than that value. So what's the root of 2? If I say, so this has got to be, divided by 2. Well, no. 1.44, so no, it wants to be square root, so sorry. Yeah. Tangent of x. So we would take the sine of x, cosine of x. That would be tangent. We could just say tangent, so pi over 2. Yeah. This is undefined here. Now, is there a better way to be doing these than just like graphing them on Desmos? Because can we figure these out like by hand somehow? That's what I want to know. Let's look up. Let's go to the almighty orb here. The orb. Let's ask it. Say, I am trying to teach myself calculus and am learning about limits of trig functions. Is there a better way of solving the problems and knowing that the limits do not exist or do, rather than having to plug them into a calculator? Or is that just how it is? Great question, and good on you for teaching yourself calculus. When it comes to limits of trigonometric function, there's a better way than relying on plugging numbers into a calculator. In fact, calculus is all about moving away from approximation and reasoning and pattern recognition. Core ideas, right? Famous trig limits, memorize these. Limit is x equals to sine x over x is equal to 1. 1 over cosine x. Tangent n over x equals tan x over cosine x times x. There's usually two reasons the limit doesn't exist: oscillation, left and right limits disagree. Look for discontinuations like asymptotes in the graph. Graphing or mentally sketching, understanding how trigger functions behave. Okay. Woo! Keep moving.
Let's think a little bit about limits of piecewise functions that are defined algebraically, like our f of x right over here. Pause this video and see if you can figure out what these various limits would.
Okay, so as we approach 4 from the right side coming in, so this would be numbers greater than 4, we would take the square roots of x. So this would be square root of x. Coming in from the left, obviously, coming out 4 from the left would be this guy over here. The limit of 4, when we're at 4, is going to be this. So 4 plus 2 is 6 minus over 3. So 2 for this guy. And the limit as we go to 2, which is going to be into here as well. So then it'd be 4 over 3.
One-sided, and some of them are
regular. 4 over 1, my bad. So 4
limits or two-sided.
So this one would be this one. This one would be this guy. This guy would be, what did I say for this one?
Limits.
Can't remember.
All right, let's start with the 4. 4 from now then would be equal to 4 plus 2 over 3.
6 over 3 is just 2, yep.
The rule to be approaches 2 of FR, and so this is going to be equal to 2. Now what's the limit as x approaches 2 of f of x? Well, equal to 2. Now what's the limit as x approaches 2 of f of r? And so this is going to be equal to 2.
When it equals to 4,
now what's the limit as...
Right, when it equal to 4, it's 4 plus 6 for minus 3, which is 2.
X approaches 2 of f of x? Well, as x approaches 2, we are going to be completely in this scenario right over here. Now into the value, which is equal to 4. Let's do another example.
Yep.
So we have a...
Okay, so g of x, as we're coming into negative 1 from the right. So it's going to be this guy. Coming at negative 1 from the left. Obviously numbers less than negative 1. Be this guy. So g of x at negative 1 will be here. So 2 to the power of negative 1, negative 2. And then at 0, coming in from the right, should be 2 to the power of 0, 1. Oh, sorry, 2 to the power of negative 1's a half. Goofball. 0. So this one says does not exist. Let's listen to these.
Right. When we are greater than or equal to negative 1, we are in this part of our piecewise function. And so we would say this is going to approach, this is going to be 2 to the negative 1 power, which is equal to 1/2.
Yep.
What about if we're approaching from the left? Well, if we're approaching from the left, we're in this scenario right over here. We're to the left of x equals negative 1. And so this is going to be equal to the sine, because we're in this case for our piecewise function, of negative 1 plus 1, which is the sine of 0, which is equal to 0.
We're approaching negative 1 from the left, so we're in the top
Now, what's
one.
the two-sided limit as x approaches negative 1 of g of x? Well, we're approaching two different values as we approach from the right and as we approach from the left.
Yeah.
And if our one-sided limits aren't approaching the same value, well, then this limit does not exist. Does not exist.
Now, for at 0 coming in from the
and
right.
what's the limit of g of x as x approaches 0 from the right? Well, if we're talking about approaching 0 from the right, we are going to be in and so we can just equal substitute x equals.
Nice. All right, ready? Let's try these guys. Okay, here we go. The limit of g of x as x approaches negative 1. So as x approaches negative 1, so coming at negative 1 from the left, we have, let me grab my pencil and paper. Right, so so as x approaches negative 1, or right from the left, or just in general, well, coming at it from the left is going to be the top way. So we need to evaluate if these are the same. So 1 over negative 1 equals to negative 1. And then 1 plus negative 1 times 2. 1 plus negative 2 equals to negative 1. Yep. Woo! Cooking, boys. Let's go. Okay. X approaches negative 2. So we need to check if these two exist at negative 2. That is our breakoff point here. So 1 over 2 times negative 2 is equal to 1 over negative 4. And then we have 2 to the power of negative 2, which would be 1/2 times 2 to the power of negative 2, 1/4. Oh, hold, but 2 to the power of negative 2 is negative 1. There's positive 1. 2 to the power negative 2 is positive quarter. And then 2 times negative 2. So I'm going to say this doesn't exist. Whoo! Yep. Don't try to trick me. Ain't gonna trick me, Con. Not today. I'm not to be reckoned with. Alright, as x goes to negative 3. As 3 from the left. So 3 from the left, as all values are less than or equal to 3. So we're going to be into this function here. So we're going to plug in 3 squared minus 1 would be 9 minus 1 equals to 8. Alright, and we're at the limit as x approaches 4 from both sides. So as x approaches 4 from both sides, we're defined at this function here. So it would just be x square root of 4, which would be 2. Yep, 4 for 4. Call me Wendy. When's the calc exam? Indiana won again? Jeez, Indiana fans must be going crazy right now. Yes, sir. Tomorrow is quiz day. Or should we take quiz today? No, let's do quiz tomorrow. Solidify our knowledge. Video here. Last video of the day. Or of the session. This calc session.
Let's say that f of x is equal to the absolute value of x minus 3 over,
we'll say, limits of piecewise functions. And we have limits, or limit at a point of discontinuity.
Okay. X minus 3. And what I'm curious about is the limit of f of x, as x approaches 3. And just from an inspection, you can see that the function is not defined when x is equal to 3. You get 0 over 0, it's not defined. So to answer this question, let's try to rewrite the same exact function definition slightly differently. So let's say f of x is going to be equal to, and I'm going to think of two cases. I'm going to think of the case when x is greater than 3 and when x is less than 3. So when x is, we do this in two different colors actually. When x, do it in green, same thing as x is less than 3, well, x minus 3 is to 1, so you're left with a negative 1. Negative 1 for x is less than 3. And I encourage you, if you don't believe what I just said, try it out with some numbers. Try out some numbers, 3.1, 3.001, 3.5, 4, 7, any number greater than 3, you're going to get 1. You're going to get the same thing divided by equal to 1. This function is equal to 1, so it looks like that, and it's undefined at 3. And if x is less than 3, our function is equal to negative 1. So it looks like, let me do it in that same color. It looks like this. It looks like this. Once again, it's undefined at 3. So it looks like that. So now let's try to answer our question. What is the limit as x approaches 3?
So at x equals 3, you get a value of 1 and a negative 1. Okay, gotcha.
Well, let's think about the limit as x approaches 3 from the negative direction, from values less than 3. So let's think about first the limit as x approaches 3, the limit of f of x as x approaches 3 from the negative direction. And all this notation here, I wrote this negative as a superscript right after 3, says, let's think about the limit as we're approaching, let me make this clear. Let's think about the limit as we're approaching from the left. So in this case, if we get closer, if we start with values lower than 3, as we get closer and closer and closer, so say we start at 0, the f of x is equal to negative 1. We go to 1, f of x is equal to negative 1. We go to 2, f of x is equal to negative 1. If you go to 2.999999, f of x is equal to negative 1. So it looks like it is approaching negative 1 if you approach from the left-hand side. Now let's think about the limit
doesn't exist
equal to
because you're approaching
0.000001, f of x is equal to something right over here does, or another way of color, f of x as x, if the limit of f of x as x approaches c from the negative direction is equal to the limit of f of x as x approaches c from the positive direction, which is equal to L.
Cool.
This did not get the same limits when we approach from either.
Nice. All right. Quiz 2 is up next. Oh boy, do we take quiz 2 right now? Do we save it, boys, or do we take it? Quiet stream today. People must be out and about enjoying their Friday. I wish. I wish. Let me tell you. Let me tell you. Take it. All right. Let's take it. Here we go. We need our pump up though. All right, you guys, get your pump up. Ready? Oh. Hold on. All right, here we go. Quiz 2. Find the limit of h of x as x approaches negative 2. So as x approaches negative 2, we need to evaluate both sides because that is the point that we are on here. So 5 times negative 2 is equal to negative 10. Negative 2 cubed minus 2. Negative 2 times negative 2 is 4. Times negative 2. Negative 8. Minus 2. Negative 10. What do we think? Do we think at negative 10? Everyone's at graduation this week? Yeah, that's probably true. I say negative 10 here. Punch it! Woo! Okay. Okay, functions f and h are graphed. Find the limit as x goes to 0 of f of x times h of x. Okay? So using our function properties, this is the limit as x goes to 0 of f of x times the limit as x goes to 0 of h of x. What's up, Ark? How's it going, dude? Welcome back in, my friend. It's good to hear from you again. Okay, so the limit of f of x as x goes to 0 is going to be 1. And the limit of h of x as x goes to 0, well, we are split here. It's in the first case is going to be coming in from the right is going to be looks like 0, and coming in from the left is going to be as we approach positive 3, right? But the thing is, do we multiply these together, or does this not exist? Right, because is it 1 times does not exist? Or is it 1 times the different paths? I think it does not exist here in this case. Because this one is going to be 1, right? What is this? Okay. Yeah, 1 times DNE. Alright. Alright, here we go. We want to find the limit as x goes to 3 for -4 over 2 times as x goes to 3. So -4 over 2 times 3 over 5. -4. -4? What do you guys think? I get -4 over 2 times 3 minus 5. -4 over 6 minus 5. -4 over 1. Alright, ramping it up here. So let's look up cosine here of x. Cox of x, pause. So cosine is defined over all real numbers, we know that. So on pi, we're defined at -1. Alright, functions f and g are graphed. Find the limit of f of g of x as x goes to -2. Okay, so this one's a little bit trickier. So we need to find the limit of the inner function and see if it is continuous at that point of f. If it is, plug it in. So I can already tell you right now, the limit of g of x at that, as we approach 2, does not exist. Right? So I'm going to say DNE here. He's him. I'm that guy, pal. So, right, we cannot take the inner function here. This inner function does not exist at a limit of x approaches 2. I was scared on that one. I was nervous. Okay, function g is graphed. Find the limit of 2 times g of x as x goes to 0. So as x goes to 0 for g of x, we have 3 times -2, -6. You're not that guy, Tim. Believe me, you're not that guy, pal. I love that move. Hold on.
How's that? How's that? How's that? Fuck you where you breathe. Okay? Don't tell me what the. How's that, pal?
Never mind, I did tell him not to.
If you guys could not do this in the store.
That sounds like.
You're not that guy, pal. Trust me. You're not that guy. Okay?
You?
Absolutely.
Absolutely.
Gonna get arrested for this?
Arrested for doing what? Just like. You're not that guy, pal. Trust me. You're not that guy.
I need like I need to cut that out, and if someone like subscribes on YouTube, I need to have like it play like an overlay of it, a video. I have to do like the code of it or something. That'd be so the guy, I love that video. He looks like a claymation.
Check out.
Ring out if you take
Okay? You're not that guy, pal. Trust me. You're not that guy.
You're not that guy. He's got a good set of hair though. He kind of looks like 25 and like 55 at the same time.
Guy, pal. Trust me. You're not that guy.
Then when you get in, it's like, okay, yeah, it's grandpa. But when you're like away, it's like, It's like, oh, it's kind of like Beachy Bob, but when you get in, it's like, oh, it's Grandpa Gary. Okay, we're running out of time. We're timed here. Oh no. Okay. Do we say -6 here? Oh. Oh, 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 oh! Woo! Nice. Do you like sunny day real estate? Is that another meme reference? If I'm not getting it, I'm sorry. Sorry if I don't get it. My bad, my bad. Ah. It's fun. That's fun. We have fun here. We like to have fun. Right, Tim? We like to have fun. Dude, Tim, did you see my message in Discord? Did you see my message in Discord? Let's take a look. All right. Let me bring up. All right. Here we go. All right. This is a big, now this is not technical analysis by any means, but I posted in my Discord in the off topic. We like to have fun in there sometimes and throw some stock plays that we think might come out. We have Apple, extremely undervalued in my opinion for the current status of the QQQ over the past month. Now, we'll see what happens over these next couple of tech earnings. But I say 195, anything below 195, rapid buy. In my honest opinion, I am going to be transparent. I do have end of June 210 calls. 210 calls. I'm currently down a little bit on them. I am holding, and I am averaging, and I am going to roll if that does not happen. All right, that's my drinking water out of a mason jar. No, it's not water. It's lemonade, Mr. Lemonade. Okay, cool. That was lesson 6 on this. We are 7% done with the course here, and we've only been doing it since this was our first week taking it, so we've only been doing it 5 days. So 5 days, almost 7% in is really, really good. Hopefully I'd like to be at, hold on, if we say up next lesson 7 here, now does it say that we moved on? Still 7%. Okay. Yeah, if you guys aren't in my Discord, you can join my Discord link down below, and consider subscribing to the YouTube channel if you're new here. My Discord is like a complete roadmap of my learning journey, and we just like to have fun in there and give you guys good resources to learn from. Okay, let's go ahead and push this up. Finished lesson. Nice. All right. You guys didn't see our video upload on the YouTube. I posted a video for the project demo for the our portfolio website. So feel free to check that out if you haven't seen it yet. Oh gosh. Bro, Tim, don't get feeling some way, Tim. Yeah, so check out the demo video if you haven't seen it yet of our website here. What language? I took 2 years of butchered Spanish, let me tell you. 2 years of butchered Spanish, that's for sure. Uh-huh. Should we do a... Mike wouldn't last a day in Cancun. Is that where Boston is right now? Isn't that where the Boston Celtics are right now, Tim? Oh my gosh. Portland Trailblazers aren't much better, though. Tim's gonna get canceled out here. Tim's getting canceled. Oh, that's funny. Okay. Which one should we do? Summary ranges. You are given a sorted unique integer array of numbers. A range AB is the set of all integers from A to B inclusive. Return the smallest sorted list of ranges that cover all the numbers in the array exactly. That is, each element of numbers is covered by exactly one of the ranges, and there is no integer x such that x is in one of the other ranges but not in numbers. For each AB range in the list should be outputted as quote A arrow B if A not equal to B, quote A if A is equal to B. I hate these stupid arrow ones. I don't know what it wants me to do. Does it want me to output these arrows? Tim punching the air right now. Tim's cooking blazers right now. Cook them. So this one gives you 0, 0, 2, 4. The ranges are 2 to 4, 6. I don't get it. What's it asking? Return the smallest sorted list. So if it's 0 indexed, so code. So it's sorted. What's up, Blankers? You have a lot of time today? I do not, unfortunately. I got my my lady friend's coming back. She's on her way here right now. I don't know what that one's asking us to do, so we'll just wait for a second. Given an integer n, return true if it's a power of 2, otherwise return false. And n is an n power of 2, exists. N is equal to 2 times the power of x. Okay, so given an integer 1, so then if we just modulo, so if we go right, if we have number, well, obviously it's an even number. It doesn't mean it's a power of 2, right? Obviously that goes in 0 times. Or like that goes in evenly. It doesn't have any remainder. So how can we... if 2 to the power of x is equal to some value. Could you solve it without loops or recursion? Okay, so given an integer n is a power of 2 if there's exists an integer x such that n is equal to some power of 2, meaning that there is a value of x. It does this. So obviously, if we square root, we root x, we're trying to solve for, obviously, so we're trying to solve for x and see if there is a value of x. Let me pull up. Okay, so integer power 2 if there's an integer x such as 2 equals. Okay. So we need to find a value of x. Obviously, we don't have to do it loose. We can I square root? Base of 2. So this is kind of like another base of 2 problem, meaning like a binary problem, right? It's not a base 10 problem, it's a binary thing. So I always suck at these problems. So what if we go, let me pull open my thing here. So what if we have like n is equal to 16? Let's go bin n. Let's print bin n. Okay. I want to see the bin function. Okay. So this is here. So let me do this. Let me see here. So let me go, instead of doing this, for I or n in range let's just say 1 to 11. 0 to 1 to 11. Let's go ahead and print out bin of n. So let's see if we can find like a commonality here. Oh no, we don't. Hold on. We want to say 2 power of n, right? Okay, so right off the jump. So right off the jump, all of these have a value of 1 here, and every other value is 0. Right? Now what if I'm just gonna do this. I'm gonna just print bin on n itself here, right? Just to see the differences. Okay, so I'll say we'll say that's a none, so as a okay. This gets a 0. This doesn't look like that. So what if I bit shift this to the left, and then if that is equal to 0, then I have a match, right? So if I bit shift this 1 to the left and flip it, or I just flip, so if I go, can I index into, can I go like this? Let's say this is going to be temp or t. Let's do this, right? And then can I index into t? Can I print t index 0? Can I print the first bit? Yeah, I can. So let's print t. Let's also print t0. Which is this guy, so the 0b. So we want to get access to this 1, so we want to print the second index. Okay, now we're getting that 1. Now, can I bit shift this? I'm not very good at this. Bit shifting. Bit shifting left shift shifts all the bits one to the left and fills in zeros on the right. So if y equals 5, if a bit falls off the leftmost edge on a left shift, does it disappear? Okay, perfect. So let's go like this. Let's bit shift. So can we do this? Can we say, I haven't read any chat here, so hold on, give me a sec, you guys. I'll catch up on chat in a sec. So let's take n. Let's say n is equal to bin n. Let's go. So then, actually, how can I get rid of the notation with bin? And there's a way to get rid of it. How can I get rid of the prefix for bin? Just slice it off? I don't want to slice it. I can either format the binary string. Okay, so then I say if I left bit shift on a raw bin return, will it include the prefix? Yes, if you shift, it will include the 0b prefix. So 5 is so let me do this. Bin n return, I'll see, true if bin n Give me one sec. Let's think about this. I'm really not good at these. I've never used really the cyclic. Now if I print t shift by 1, let's do So this is a, so if I have to int the t, no. So how can I, hold on. So t. Let me do this. I just want to see what it prints out. Oh, I'm so dumb. Why am I slicing up to the third character? Am I trolling? I'm doing it again. What am I doing? 3 beyond. Am I tripping? Hold on. What am I? Hold on. Let me just go back. I'm losing my train of thought here. We want print. So let's print bin n here first. Let's see what we output. Okay, 01B, B01, B11. Okay, we want to get off that. So let's print bin, slice off the first 2 characters. Okay. Now I'm gonna slice off the first 3. I'm gonna call an int conversion to this. And I'm going to save this as n equals this. If n equals 0, we'll return true if n equals false. So before we do this, I'm going to just print n. Make sure we have zeros in there. Okay, so I can't convert an int with a base 10. Oh, so if you slice off oh, interesting. My idea is that if I just slice off the 1 and evaluate if that value is 0, like in mathematically, then I have it here. Right? That's my like initial thought here. Slice conversion of a binary is not possible. Oh, dang. Okay, so then let's just say this. If we can't loop over all the values, can I say what does the all function do again? Python all function. The built-in all function when all elements are iterable are true.
Id Software presents Doom: The Dark Ages. Available now.
Rated mature.
I mean, that would be a loop, right? Just basically saying. How can we do this without loop? You did it with a while loop and a sin. That gives me all zeros. If it is, right? So in this case, just give me a blank string. And it's all zeros. So if it's all zeros, I got it. If it's a blank string or anything else, then it's not. Now, what happens if what's it called? Is it called char n? To put it back, is it char n? Oh, chur. Stir object cannot be interpreted as an integer. Right, so I can't. If I go binary, how can I go back? How can I go back to an integer from a binary? And slice convert a Can you just, you have to just do it separately? No, invalid literal base 10 int. But if I slice and even more, on copy, if I take a copy of n, no, we still can't take a base literal for int. Oh, I remember right. The int function has to take in. I remember this from a past leak code problem. Remember that the int function has as an additional parameter of a base you can provide. It's in my notes here. Let me slice off the first two strings. Or the first three, we want to take all of off. We want to int. Let's say if for n.
With Asana, AI teammates can help level up your goals by connecting them to relevant projects, so every team knows their role in the bigger picture. Asana, the #1 AI work management.
Trying to just do some debugging here. So, come on, let me skip the ad.
Choose to lean into it. Every Mazda is engineered to give you effortless control.
Okay. So we're going to convert to a binary and take a slice of 3. Why can't I do this conversion invalid base 2 with a string? Okay, sorry, yeah. So if it's a string, return false right away. Right? I mean, we could, so right, and then else we'll convert here and we'll print. So let's see what happens. 0, 1. Okay. Return true if n equals to 0, else false. Show me the money. Show me the money. No. Oh, one test case. No. One test case. The last test case. Oh, no. Can you just stick this here as well? Or can we stick this a better place? Obviously, we could put it here. Oh, it's true. Sorry. So if we return on a... Hold on. Hold on. Trolling, dude. Trolling. So let's say in the range of 1, we slice that off, we got 0. So let me say n equals 1. Let's say print bin n here. 0b1. Oh. So if n is we want to return true here if it's a blank string, meaning that n equals 0. Oh, gosh. Right, so if 0 is also blank string. So we could just say if n is 0 right out front. Is that cheating? That's what I'm talking about. That's what I'm talking about. Come on. It's not the prettiest looking code I've ever seen. Mike, return true. Are you kidding? Tim was like, bruh, like watching that, like, are you serious? Sorry, I had to return true. I forgot that when you have when you return 0 on 0, you return false. Bruh. All right. Sweet, we got there. Yes, sir. Now, is there a cleaner way of doing it? Let's think. So, there's no difference, right? If n is equal to 1, we print out bin 0, 1. Now if we go here, 0, 0. So could we also have chosen some arbitrarily large power of 2? But right, past our constraint. Could we have chosen a power of 2, this guy here, 2 to the power of 31, and done a conversion? Can we have done this? So we do need that base case then. Tell me I'm not the smartest guy ever. Oh, dang. So negatives. Return true. Is there some sort of edge case we have to do for negatives here as well? Can you do this approach with this as well? Oh, you're using that bitwise and? Yeah, I don't know these bitwise operators as good. It's interesting. I'm gonna go to my solution or my submissions. Hey Wolfie Master, how's it going, dude? I'm gonna take my code here. I'm gonna throw it over here and say, this was my solution for Power of 2 leak code. Nice, you're thinking you're doing it. You sliced off the 0B in the first one using clever. Oh, interesting. So it says you can clean it up by doing this. So you can do it like Anand said, is the bitwise manipulation using bitwise and bitwise and. Or you can do it my way, the other, not this way, hold on. The other way I had, but we can clean it up even better and say return bin slice 3 equals string. If n is equal to 0, return false, else return bin n sliced is equal to a blank string. That works too? Hold on. I gotta see if this works. So you do return bin n, you slice off the first 3, and you say it's equal to a blank string. No. Yeah, why would it say that? Why would it say that? That's so goofy. Yeah, that's dumb. I'm gonna show it my other approach here. I'm gonna say this doesn't work for negatives. You're checking if n divides evenly, which is smart because only powers of 2 will do that. For example, positive values, it works. Because powers of 2 are always positive unless you... So you just have to add a fixed positive check then. If n is less than or equal to 0, all you have to do is that. I am smart. Come on. I am smart. How about that? Eat that. Now we can even remove this. Throw that right there. And then, boom. How about that? I like that too. Nice. This was, I kind of took this one from a previous leak code problem we did of a similar format where you could take the constraint and divide it down by that for a was it the square root problem? The perfect square problem? I can't remember. Do you guys remember which one that was? Like get caught up on chat. What's important is that a power of 2 is 1 followed by all zeros. Yeah. So that's the when I first did it, that's the first approach we were trying. So which is here where we slice off. So when I was in Python here, I noticed I was like, okay, all of the powers of 2 are just 1 with preceding 0. So let's just slice off the 1 and check if it's a value of 0. So that's what I did at first. And then I thought, okay, well, there's also another approach, right? Is there you can use the constraint to your advantage with powers of 2. All powers of 2 will divide evenly into that maximum constraint. So that's this one here. Okay, so now, so what happens here is any number 2 times but only has 1 bit set. For example, n equals 8 is 1, 0, 0, 0. So when you do n minus 1, you get 7. You get 0, 1, 1, 1, 1. So now you have to simply, but now you can simply use bitwise and to get all zeros. Okay, so you just do minus 1 to convert the first one. And you use bitwise and with the original n so that the bits line up. Oh, I got you. Okay. So it's slowly but surely these bitwise functions are getting better at them. They're definitely trickier than normal operators for sure. They don't come up as often in just normal programming stuff. At least I'm not manipulating bits in memory and stuff. So Python things. Let's look at the whiteboard. Okay, so you're saying that by taking 8 as 1, 0, 0, 0, subtracting equals 7, which goes to 0, 1, 1, 1, you use the bitwise and ampersand, giving you 0, 1, 1, 1, so that this evaluates out to, okay, 0, 0, 0, 0. And then you check return. Yeah, I know you can do that, Blankers, but it's all right. Tomato, tomato. Right, he's saying that you can just, it automatically returns a Boolean. Right, so you don't even need the checks, but it's easier for beginners to kind of follow along if I have it like this, being on stream. Right. Invalid printable character. Mr. Leaving is hard. Right. If you guys remember bitwise and if these line up and they're zeros, it's 0, but if both of them are 1, it's 1, right? With bitwise ampersand 0 and 1 returns 0, but 1 and 1 returns 1. Yeah, okay, perfect. Bitwise actually the LeetCode problems, they use these bitwise functions quite a bit from what so it's good to kind of get familiar, get more familiar with them. All right, you guys. Hey, Nitish, how's it going, dude? We solved that LeetCode problem. That wasn't too bad. That was not too shab. Let me check where my lady friend's at. Okay, you guys. I think I'm going to wrap it up here. Thank you guys so much for joining me. We hit 2180. 2180, boys. I appreciate it. Thank you guys so much for all the support. Truly, truly, truly. Bitwise functions are how the CPU actually handles things, so you know it's crazy fast. Yeah, and just Jack, I want to talk to you about that. So, I was watching this MIT maker submission video, and this guy made a huge computer in Minecraft, and he said he implemented bitwise operators and stuff. So when you're developing like an operating system, you create these operators on the low level, like addition, subtraction, multiplication, bitwise operators, and then also like the for loop, right? How is the for loop and like the loop created on the low level? Like how is that written into bits and bytes or whatever in terms of lady friend? Now we know you're lying. Wolfie Master trying to flame me. Hey Nugs, how's it going? Does anybody know like how that works? I'm very curious. Called a jump. Wolfie Master says JMP, special register. And so am I like talking about the right thing here? If I'm not, correct me. You can, and a jump can bring you to another spot in code. Oh, okay. So do you create like these memory objects and then you jump from pointer to pointer, basically kind of creating a loop, and then you jump back to the same memory object? So you reserve a piece of memory based on how many steps in your for loop or in your loop, and then you jump using pointers from memory location to memory location, and then it circles back. So is a loop then just a memory like linked list? Compare sets a bit in a register that jump will go one spot to another. Yeah, those pointers are called labels in assembly. What you need to do is create a bit addition, then you move to implementing an adder. What you need to do is create bit addition and then move to implementing an adder. You can do all sorts of things using the adder, like subtraction, multiplication, division, repeated subtraction. Interesting. This sounds really interesting. How do people figure this stuff out, dude? Making rocks talk? What? Isn't that crazy? That's really cool. People are so smart, dude. How do they figure that out? All right, you guys. Yeah, so this one is a little bit shorter than normal. I do apologize. Having, Friday night is, I normally go longer on Friday nights. My lady friend usually comes back on Thursdays, but she's having to, work on Fridays now for just a short little bit. Fridays are the day I have to cut it short because I'm going to spend some time with her. But I will be back tomorrow. So my goal is I'm going to try to come on tomorrow morning for a little bit and, do a morning session. I'm going to hang out with my lady friend, and then I'll also come in for an afternoon session. So hopefully we can, interact and get some more of the international and East Coast of our subscribers in here for that. So what time works best for you guys in the mornings? I'm on PSD. That's how people implement CPUs in games like Terraria. Interesting. Okay, let's check my GitHub and make sure we got a contribution for today. Make sure we got our contribution for today. Yes, we did. All right, you guys, this weekend we're going to do a lot of project work, so make sure you guys come back. I know during the weeks we've been doing a lot of studying, especially as we've been starting up calculus and doing calculus. Yeah, the whackathon, we got to plan that out. Just look the innocent eyes. What blinkers? Just look the innocent eyes. What? Y'all are getting cryptic on me. Anyways, I'll be back tomorrow. I feel bad, leaving early tonight. I had fun tonight. One assignment in school, I remember we had to reverse engineer assembly code, but I failed. I will stop by again if I can. Awesome, Jack. Thanks so much for coming in, dude. Yeah, join the Discord, link down below. My GitHub? Yeah, I've been it just goes to show you guys coding every single day. We've got 17 repositories so far, full of just mix of projects and books, like quite a lot of like Pro Git second edition here. We have like chapters on chapters of notes here. Oh, researching on my current undergrad. Oh, nice, Jack, dude. Yeah, my name's Michael. I'm 26. I got a degree in human biology and a minor in chemistry. I work as a formulation chemist for a biotech company where I make biological controls that are used in like patient diagnostics and research and advanced immunoassay analyzing. I do a lot of like matrix computations, like using like two-dimensional arrays to compound various solutions together to predict their theoretical concentrations in bulk. And so so currently at work, which is something really cool, is I pitched my work like an automation. I told them, I can code, and so I wanted to code a project, and so they allowed me to kind of make this kind of jump, I guess. And so I'm coding an actual automation for one of these matrix and stuff. So it's really cool. So I've been getting a lot of practice with that, but I've been coding for 11 months now. We've got 5 projects on our website. We've built, a website with React. We've built chromatography simulator. We've built a small business manager. This is a community project that we have open source right now. We built it ourselves, but then we opened it up to everybody once we completed it for more improvements. We've got our task manager, our CLI, and our inventory management system. And so right now we're working on our Spectro Sim. So our Spectro Sim is our Python project that we wrote a web scraping script here to actually get data via API and then parse that data looking with regular expression, looking for some groupings and matching out some data. So for example, we're looking for benzoic acid from this API from PubChem database, and we're actually extracting out the individual we're parsing out the individual data from that return. So we got the name benzoic acid, the CID, the solvent used, the lambda max, and the epsilon used. And then with that data, we can compute. I wrote this algorithm, right, using Gaussian distribution curves, like a normal curve, and then the Beer's law, which is a chemistry, law or whatever, or function, to actually compute these absorption spectroscopy simulations. And so this is what we wrote here. So we're going to, this weekend, we are going to launch up a front end, hopefully, and get this all working together now that we have a database and such. So hold on one second, guys. My girlfriend's calling me. All right, you guys, I'm sorry. I appreciate you guys being here and joining me. Sorry to bail out on you guys so quick, but please subscribe so we can talk in the future and join my Discord. I stream every single day around 7 p.m. PST, but tomorrow, or after my 9 to 5 job, but tomorrow on the weekends, I'll stream kind of double header sessions and whenever. So be in the Discord for announcements for when I go live. But thank you guys so much for being here, and I appreciate you. Check out my projects on michaeldeming.com. And yeah, I'll see you guys tomorrow. Bye, guys. Have a good night.